Okay, we're on.
I'm sorry, turn on your mic.
Picky.
Okay, I got you.
Okay, I'm on. I just wasn't talking. Okay, how was the test? Did you enjoy it? One never enjoys tests. I did get a couple of emails about the first problem. I think I'll take just a bit of time to address that. Since I got 2 emails, it means probably half the class is interested in the problem. The first problem was a Monty Hall sort of problem, which is the reason that I gave it to you. The question was as follows. There were 2 identical dice. Remember, I stressed that they were identical. I believe that they were ivory. Both die were ivory with black dots on them. You recall that? The dice were rolled. One of them showed a 6. It did not say the first die showed a 6 or the second die showed a 6. The English is very clear. One of them showed a 6. It doesn't specify which one, but one of them showed a 6. So it would be akin to rolling it and some observer on the other side saying, one of these dies is showing a 6. And then your problem is to find out the probability of the other die showing a 6. Or not showing a 6, I believe was it. Right? So the ambiguity, at least I saw in the email, was whether or not the die that had the 6 on it was identifiable. And I tried to be very clear in the statement of the problem that the die were indeed identical and were undistinguishable once rolled. And also the English, one of the die, not the first die, not the second die, but one of the die showed a 6. So there is no ambiguity in the statement of the problem. So with that, would anybody like me to work the problem with that explanation of the problem? They say that many times the solution of a problem has 90% of it the statement of the problem. So maybe now I've stated the problem that it solved. Would anybody like me to elaborate further on the solution?
I saw the solution, and that makes sense. What I don't understand is why a different way of solving it doesn't work. I agree with the answer. But the way I thought of it was, if I'm in a dark room and I roll 2 die, and I shine a flashlight around and I spot one and that one has a 6.
Yes, that's an equivalent way of doing it. Yes.
And then there's another die in the dark somewhere.
Right.
And I can't believe that the odds are not 5/6. That the number of dots showing on that other die in the dark are not 6.
I understand what you're saying.
It's not equivalent.
But it's not equivalent.
So
the reason it
what's
isn't
the
equivalent,
difference in the information?
The difference in the information is the die that you get with the flashlight, there's a 50-50 chance that you get on the first die and the second die. And in your way of viewing it, you always look at the first die. It's much like if there was a problem of rolling a red die and a green die, and the green die came up a 6, what's the probability that it's not a 6 on the red die? Now in that case it's independent and it is 1 out of 6. But if the die are indistinguishable from each other, then it does make a difference.
Then say you take your red die and throw them across the wall, and the observer on the other side says, one of them's a 6. And then I would say, well, there's a 50% chance that it's the red one, and in that case, there's a 5/6 chance that the green one is not a 6. There's a 50. You see where I'm going?
Yes, but if you throw the die, I'm hoping that the microphone's picking up the dialogue here and just not my responses. But if you throw a red die and a green die across the wall, and the observer says one of them is a 6, then all of a sudden the dies become indistinguishable again. Because you don't know if it's the red die or the green die. So it's
a probability to both cases. I explicitly, took away my knowledge of whether it was the red by saying there's a 50% chance it's the red and 50% that it's the green.
The question is not whether it's red or green, but whether you have specified it's the first die or the second die or one of the die. That's 2 different types of a priori. A priori is beforehand information. And it's the assumption that you have. The assumption of the problem stated one of the die was a 6, not the first die was a 6 or the second die was a 6, but one of them, either the first one or the second one, was a 6th, was 6. If there's still challenges, see me and we can
Okay.
we can battle that. Okay, sounds good. Okay, so hopefully, yeah. If anybody wants to talk about the maybe I should work the problem. Let me work the problem. The problem number 1 is, here are the possibilities of the die coming out. Here's a Venn diagram, if you will, of all of the possibilities of the dies. Of the dies. The dice, not the dies. Huh. Okay. Now, there's 2 interpretations of the problem, and if you're very loose on the interpretation of the English, which of course we can't be, one of them is that we can distinguish between the 2 die. The first one is the probability that die number 1, that die number 2 is not equal to 6, given that die number 1 was equal to 6. That's one of them. The other one is the probability that a die is not equal to 6, given the other die is equal to 6. And this should be one die is not equal to 6, given the other die is equal to 6. These are 2 separate problems with 2 separate answers. And here we get into the distinguishing between the 2. Clearly, in this first one, the probability that die number 2 is equal to 6, given that die number 1 is equal to 6, this event is independent of this event, so therefore, given this information, gives you no information at all. So this is clearly equal to 1/6, correct? Same thing. Okay, you're right, 5/6. Thank you. The second one is the probability that one die is not equal to 6, given that the other die is equal to 6. What is the probability that the other die, that is, one of them that you have observed, is equal to 6? It is equal to all of these possibilities. All of these possibilities correspond to one of the die being a 6, right? Right? So, and then what is the probability of the other die not being a 6? Well, given that one of the dies is equal to 6, the probability of the other die not being a 6 is equal to this, or this, or this, or this, or this. This is the only place where both of them are equal to a 6. And so a total, in our new Venn diagram, if you will, is we have a total of what? 11 possibilities where one of the die is 6. Now, the OR is an inclusive OR. That means the first die is a 6, or the other die is a 6, or both are 6. That would certainly take into account that one of the dies is equal to 6. So we have a total of 11 possibilities. And out of those 11 possibilities, there are 10 possibilities where the other die is not a 6th. Okay? So the ambiguity that I see in the working of the problem is the interpretation of either this or this as the statement of the problem. Okay? In this case, you can distinguish between the 2 die when they're rolled. In this case, you can't. You roll the 2 die, one of them's a 6. Either the first one or the second one, you don't know which one, but one of them is a 6. Does this help at all? No? Okay. It doesn't help one person. Okay. So this is the differentiation between the 2. Okay. Let's return to the lecture then. Let's talk now about joint Gaussian random variables. Now, this is some of the material that you've seen before, but nevertheless, I think that we should probably look over it. We looked at last time in 2 random variables of having 2 random variables which were referred to in terms of descriptors of random variables at 2 at a time. The new descriptor we came up with was the correlation coefficient. Let me get my pointer. Where's my, oh, there it is. the correlation coefficient, and the correlation coefficient is equal to the covariance divided by the individual standard deviations of each of the marginal random variables, which in computational form can be written as the equation that I'm talking about. But the correlation, what does correlation mean in the English dictionary? If you were to look it up in the dictionary and use its dictionary definition as opposed to its mathematical definition, if two things are correlated, it means that one is related to the other one, right? So that's what the correlation coefficient is attempting to do. In fact, correlation has the flavor of independence and dependence. If you were to look up correlation in the thesaurus, and you were to look at all of the words for in correlation, correlated in the thesaurus, you would probably find the word dependent in there, wouldn't you? And for uncorrelated, you would find independent as synonyms. They're both attempting to measure the same sort of thing, except it turns out that correlation is a much broader category than independence is. Correlation is a much broader category than independence is. So therefore, if we have two random variables which are not correlated, their correlation is 0, means that in accordance to this measure, which is a very broad one, that one has nothing to do with the other one. It's not as strong a statement as that they're being independent, but if they're uncorrelated, one has little to do with the other one. So this is an important number here, and which is the correlation coefficient. Now, the next thing we'll talk about is the joint Gaussian random variable. And here we have two random variables, x and y. Both of them have a marginal, which is a Gaussian random variable, and those marginals have parameters m1 and sigma 1 and m2 and sigma 2. However, now, so individually these are Gaussian random variables, but they're related in some fashion. Price of gold, price of silver is the example that we kind of use. There's also a relationship between the two. The only thing that you need to know in order to characterize the relationship between the two, if they're Gaussian random variables, is this correlation coefficient rho. So in a joint Gaussian random variable, we have 5 parameters. We have the mean and the variance of the first random variable, the mean and the variance of the second random variable, and then the correlation coefficient, which describes the mix between the two. And those 5 parameters totally defined the joint Gaussian random variable. If you recall, if we integrated the joint, we got the marginal. And indeed, if we integrate this joint, we will get a Gaussian marginal. In fact, I think you can see if we were to integrate this and we were to get the marginal with respect to x, it would be a Gaussian random variable with a standard deviation of sigma 1 and a mean of m1. That's what it would turn out to be if we were to compute the marginals. Now the question is, what does this look like? We know that these two-dimensional random variables have density functions which kind of look like landscapes of some sort. We're going to deviate a little bit here down a side road in order to explain this. We're going to make an observation about so-called contours. We're all familiar with contours such as they exist on a map telling us about elevation or temperature or some other thing. Here's an interesting observation. Let g of x have contours. So this is a function g of x. And what we have here is contours of g of x. These are the locus of points for which g of x has an equal value. For example, along this black line, I don't know if you can just, yeah, I guess you can see it on the screen. There's a dark blue and a black line. Along this black line, suppose g of xy is equal to a, where a is some number, say 2 or 14. So along this line, we have an equal value. What is interesting about this is that any function of g of x has the same contours. Now, the values on the contours are not the same, but the contours are the same. In other words, if I were to look at g squared of x, what would be, the contour would be exactly the same, but what would the value be on the contour? A squared, right? If I was to look at the function g squared, not g, but g squared, I would have exactly the same contour, except that along the contour, instead of a value of a, I would have a value of a squared, right? Same thing if I were to do any function of g. The contour would be the same, but the value along the contour would be different. So if I took an arbitrary function of g of x and a, for example, f is equal to the square, then the value along this contour is no longer a, it's equal to f of a, whatever that function is, but nevertheless, the contour itself remains exactly the same. So this is an interesting observation that we can use. It's a very general observation, but it's one that we can use in interpretation of this joint Gaussian probability density function. So let's take a look at the density function, and what we would like to do is get a handle on what the contours of this density function look like. Well, the only place that this is a function of x and y is within these square brackets here. Do you agree with that? Within the square brackets, that's the only place it's a function of x and y. Everything else is a parameter of the operation. So I maintain that the function f, if we could scan back here, that this function f of xy has the same contours as does the equation in the bracket here. Why is that? Because I can get the equation in the bracket by taking the log of f and then taking a bunch of junk to the other side. And if that f is equal to a constant, then the log of f times all this other stuff is also going to be equal to another constant, and the contours are going to be exactly the same. So therefore, this joint probability density function has exactly the same contours as the parameters, as the equation which exists in the square brackets, because that's the only place where it's a function of both x and y. So what I have done here is, again, applied the contour. The contours of f are the same thing as the contours of the log of f times a number, and that is equivalent to the relation that we have in here. Well, if we look at this equation and we ask what is the contours of this equation, we see immediately that this is a quadratic of sorts and indeed describes an ellipse, or in fact a family of ellipses. If we were to set this equal to a constant, depending on what the constant was, we would have a different ellipse. The larger the constant, the larger the ellipse. In fact, if we were to plot this, it would be a big elliptical bowl, and the big elliptical bowl would go to 0 at x is equal to m1 and y is equal to m2. You agree with that? If we set x is equal to m1 and y is equal to m2, this whole function goes to 0 in the bowl. And then the bowl begins to go outwise, and if we were to take a horizontal slice of that bowl, we would obtain an ellipse. So therefore, we conclude that the overall shape of this Gaussian random variable has contours which are concentric ellipses. Now, it's the bowl. This g of x of y is the bowl. Now, that's the contours. F is clearly not a bowl. F is more like a Hershey drop. In fact, at m1, m2, it's a bump. It's maximum at x is equal to m1 and x is equal to m2, but the contours are the same as the bowl. So this is roughly the way we can visualize the joint Gaussian probability density function, that the cross-section is an ellipse, and this ellipse is really determined by this, this correlation coefficient, this rho. And one can show by looking at the math, we won't go through the details, that the angle of this ellipse's major axis from the x-axis is given by the equation which is shown here, this arctangent equation. So this gives the eccentricity, or if you will, the tilt of the Gaussian random variable at that point. And then you can visualize the Gaussian random variable as being a bump, and the bump has this sort of cross-section. Okay? The marginals are one-dimensional Gaussian random variables, in the sense that if we took this two-dimensional bump and we were to do a projection onto the x-axis, we would get a Gaussian random variable with a mean of m1 and a standard deviation of sigma 1. Similarly, if we were to do the projection this way, we would get a Gaussian random variable with a mean of m2 and a standard deviation of sigma 2. So the marginals are the same. But notice in general, you cannot get the joint from the marginals. You can under what condition? That they're independent of each other, right? Let's look at this angle here. Notice what happens if rho is equal to 0. If rho is equal to 0, what does that mean? It means that they're uncorrelated. The correlation coefficient is 0, so they're uncorrelated, correct? If they're uncorrelated, what is this angle equal to? It's equal to 0, isn't it? And in fact, what happens to this ellipse now is it is aligned with the x and y axis. And in fact, if we go up to the original expression here and we were to set rho is equal to 0, this entire middle term goes away, and this rho goes away, this coefficient in the front goes away, and we are actually left with the following. This is what we're left with if we set that correlation coefficient equal to 0. Now, what's interesting about this is you'll recognize this is now separable, isn't it? Okay? So this is equal to actually f sub x of x times f sub y of y, which is equal to the marginals. This is a peculiar and unique property of the Gaussian joint probability density function. For a Gaussian random variable, if the correlation coefficient is 0, then the random variables are independent. This is not true if we talk about a joint Cauchy random variable, a joint exponential random variable, a joint Poisson random variable. Only with the Gaussian. Rho is equal to 0 implies x and y are independent. And again, we have only shown this for a Gaussian. There might be some other ones, but in general, it's not true. It is true for the Gaussian. Let's look at the second question. Well, the first question, the marginals are 1D Gaussian random variables. The second one is, do Gaussian marginals imply a joint Gaussian random variable? This is an interesting question, which was actually, it was posed to me. There's a physicist named Leon Cohen, and he gives talks on joint, time frequency representations. In fact, there's a class of time frequency representations like spectrograms that are named after Cohen. And he asked the question, if we have Gaussian marginals, he asked this in a lecture, does this mean that the joint random variable is Gaussian? And I'll ask you this question. Suppose we have a joint random variable. Okay, we don't know what it is, but we do know its marginal is a Gaussian here with a mean of m1 and a value of sigma 1. And we know also that its marginal with respect to y is a random variable, m2 and sigma 2 corresponding to its dispersion. Are we assured that if this is the case, that this will be a Gaussian? Anybody hazard any guesses? You understand the question, first of all? In other words, will this be a joint Gaussian random variable of the type that we talked about? Or do there exist other random variables that would also give you those marginals? It's an interesting question, and one I'll let you think about. Another one is, the last question we have in our sheet here on this slide is, when is a joint Gaussian random variable a line mass? Now, let's look at this angle here. Well, no, let's do this. Let's go back to our expression. There's a number of ways we can actually look at this. No, actually, I want to go back to the line mass because I want to explain it in terms of this ellipse. Now, this ellipse can be at any angle, and this ellipse can have any major and minor axes. Can you envision with me the case where one of the axes, the minor axis, becomes so small that it becomes 0, and that the major axis begins to spread out over the line? Eventually, we will asymptotically generate a line mass in such a case. Does that make sense? That we could take this ellipse in a limiting case and squeeze it together this way, and, well, actually, we don't need to spread it out this way, but just squeeze it together this way in order to get a line mass. and indeed it does become a line mass. Can anybody tell me what the relationship between the two random variables becomes when we have a line mass? The correlation is equal to 1.
Function of x.
Y is a function of x. Yes. If they're joint, yes. In fact, that's exactly true. If y is equal to something like a constant times x, let's say a constant times x, and then we can actually subtract off other constant. If we have a relationship like this, it does turn out that if x is Gaussian, y will be Gaussian also, right? But x totally determines y. And this is a similar flavor to the line mass problem that we talked about last time. And when we do have a relationship like this, where x is a Gaussian random variable, y becomes a Gaussian random variable, they are joint Gaussian random variables, but their density function is described as the line mass. Very good.
Well, when you say y is a function of x, y has to be a linear function of x, right?
For this particular case, in order for them to be Gaussian, because if we were to have y is equal to some function of x, x could be Gaussian, but y would not be Gaussian. We're talking about joint Gaussian. So therefore, y has to be Gaussian. The only way that you can get another Gaussian from a Gaussian is through the linear combination. Okay. Otherwise, the line would be skewed along along whatever trajectory that function corresponded to. We extend here, like the Hottentots, from, I told you about the Hottentots. I could only count to 3. We can only visualize in 2 dimensions, so we go 1 dimension, 2 dimensions, many dimensions, because we can't comprehend above 3. So we can go to n jointly Gaussian random variables where we no longer have the ability to do accurate visualization of the problem. Here, if we have n random variables, n is the number of random variables, and we say that they are jointly Gaussian to each other. So visualize with me, if you will, a vector of n numbers. They're each random variables, they're each Gaussian, and they're also jointly Gaussian, which means that the entire vector x can be characterized in an n-dimensional probability density function given by the f sub x. Here is the general equation for it, and you'll notice that it is in matrix vector form. You will note that we have a matrix here which is called K, and this is referred to as the covariance matrix. And let's talk about this. M, which is the mean of the random variable, is the expected value of the vector. And K, it kind of takes the place of the variance, except now we have to look at the variance not only between a random variable in itself, but the random variable in its neighbor, hence a covariance. So, this is wrong. This should be a y right here. This should be the expected value of, no, this is right. Never mind. This is right. This is totally correct. This is totally correct. Now you'll notice, first of all, when we multiply two numbers together, or two vectors together, we either get a scalar corresponding to the inner product, or we get a matrix corresponding to an outer product. This is a outer product sort of matrix that we're multiplying this vector times this vector in order to get a matrix. So K is an n by n matrix. You'll also notice that if K is an n by n matrix, that we're assuming it's invertible here. And we're multiplying both sides by a vector in such a manner that the total matrix vector equation becomes a scalar. Even though the exponential is represented in matrix vector form, if we were to multiply this out, we would come up with a scalar. So it's e to the minus 1/2 times a scalar, where the scalar is given by this vector representation. Yes?
How come two jointly Gaussian random variables don't have, I mean, why isn't the covariance there a 2 by 2 matrix?
It is. And in fact, let me elaborate. If you were to look at n is equal to 2, you were to compute this K matrix, and you would find out that this K matrix contains what? It contains in the upper left-hand corner sigma 1 squared, the bottom right corner sigma 2 squared, and on the off diagonal something with the autocovariance. And if you were to multiply those out, you would exactly get that quadratic. So this is the general expression for the matrix. Now, let's see if we can generalize our visualization of this thing in dimensions. We first of all have this K matrix. This K matrix characterizes the shape of the density function. You might imagine that in 2 dimensions we have an ellipse. What do you think we have in 3 dimensions? We have an elliptical cloud, right? And in n dimensions we have a type of elliptical cloud. Now, where is that cloud centered? That cloud is centered at the vector m1. So in other words, there is a vector out in the space, and bloop, that vector out in space is where that cloud is centered. The cloud itself has contours corresponding to hyperellipses, and the actual shape of the hyperellipses is determined by this covariance matrix K. Exactly how might be a little bit difficult to determine, but it is determined by this matrix K. So the matrix K determines, if you will, the eccentricity, the rotation, however you want to think about it, of this Gaussian cloud which exists out in space. So this is how we characterize n jointly Gaussian random variables. And one of the nice things about Gaussian random variables is that they are so wonderful to deal with analytically. We will have developed by the end of this course a large tool chest in which we have a number of different procedures that we can throw at Gaussian random variables because they're very special in many ways. We have seen, for example, that in the 2-dimensional case, if we have uncorrelated Gaussian random variables, they're independent. This is only true of a Gaussian. The Gaussian will also rear its head again when we talk about the central limit theorem, which is where Gaussians happen. Okay, let's then talk about characteristic functions. We have seen in general the definition of an n-dimensional characteristic function. Here it is for a Gaussian. This is the characteristic function of the random variable, random vector x as a function of omega. Now, omega is omega 1, omega 2, omega 3, omega 4. So the characteristic function is also in an n-dimensional omega space. And if we were to look at the characteristic function, it would be e to the minus j omega m. M is the mean. And again, we're taking the inner product here so that the result of this vector-vector multiplication is a scalar. Minus 1/2 times this covariance matrix with omegas on either side. So this is a quadratic form in the characteristic function. This is the short vector notation for the characteristic function. If we were to write it out in longhand, we would get this result. I notice there should be a j before the summation here. See where my pen is at? There should be a j before the summation here. J should be right there. So this becomes then the longhand notation. If we were to take this matrix vector equation and we were to write it out in longhand, we would get the second equation. So just like in the spatial domain, the characteristic function is quadratic, such is the case here in the other domain, in the frequency domain also. Okay, any questions on that? No questions on that. Okay. How did I get all the way? There we go. Okay, the next topic that we have then is functions of several random variables. We have taken a little bit of time talking about a function of 2 random variables. I'm sorry, a function of 1 random variable. We're going to talk now about functions of several random variables together. We have types of transformations. We've talked about a single function of n random variables where z is equal to a function of x. And in fact, we spent time on previous lectures talking about where this g of x in 2 dimensions was something like x1 times x2, or x times y, x divided by y, x plus y. We found out x plus y, if the random variables were independent, corresponded to a convolution. But in all such cases, a number of random variables in the vector were aggregated or combined into a single number. Now we want to look at a case where we have a whole bunch of these random variables, and what we're going to do is we're going to aggregate them into a bunch of more random variables. much like if we took a random variable and we multiplied it by a square matrix, we would get a bunch more random variables, right? And given the joint density function for this, how do we find the joint density function for z sub k? So we have covered a single function of n random variables. Now we're talking about functions of n random variables. Here's the concept. We have functions of n random variables. Z sub k is equal to some function of the random variable, but each random variable corresponds to a different function. Like z1 could be x1 times y, or x1 times x2. z2 could be x2 divided by x1, etc. So each function can be totally different. So z sub k is equal to g, a nonlinearity operating on all of the random variables. We will assume here invertibility. We will go away from invertibility in a little bit, but right now we'll assume invertibility. This is much like we did with the one-dimensional case. In fact, this is a generalization of the one-dimensional case. So we have xk is equal to h of z. So in other words, if we were to have up here z is equal to a function of x and say that relationship was by a matrix multiplication, how would we get back x from z? Multiply by the inverse, right? That becomes an invertible function, assuming that the inverse exists. And inverses of matrices always don't exist, but we're assuming that that inversion does exist. Suppose that each of the z's was equal to e. Z sub k was equal to e to the xk. How would we get back the original function? By a logarithm. That would be our inverse function. So we're assuming that we can get this function in a forward fashion and that there's no loss of information. That once we have the z sub k's, we have sufficient information to regenerate the x sub k's again. This always isn't the case, but it's an assumption that we're going to make. So the result that we obtain is going to be conditioned on this function. We define something which is called the transformation Jacobian, and this is a script J. It's supposed to be a script J. It's the Jacobian of x, and sometimes it's written with a eye towards electromagnetics, where you take gradients and div grad curls and all of that using an inverted del. So it's del sub x of z. Anyway, the Jacobian is a matrix, and it is a matrix corresponding to all of the different partial combinations that one can have of one random variable with respect to another random variable. So you can see z1, x1, z1, x2, z1, x, xn. We're having n random variables here. Same thing for z2, etc. So you can see it's a matrix of all possible combinations. That's referred to as the Jacobian. So with that in mind, let's look then at the density function for z as a function of z. It is clearly going to be equal to the density function of x evaluated at all the values of z. This is just a different notation for this expression. However, what is z1 equal to? z1 is equal to h1 of z. What is z2 equal to? h2 of z, etc. And we divide then by the magnitude of the Jacobian. This is equivalent to dividing by the differential in the one-dimensional case. Remember, in the one-dimensional case, we had that the derivative was equal to 1 over the derivative of the inverse. Do you recall that? We have a similar sort of situation here, where the Jacobian of z is equal to 1 over the Jacobian of x. The Jacobian of z with respect to x is equal to the reciprocal of the Jacobian of x with respect to z. And the magnitude means taking the determinant of the corresponding matrix.
You have here that z has the same length as x. Is that the same number of elements as x? Is that important here?
Yes, it is important. In fact, it's necessary for invertibility if you think about it. If you have more elements in z, then you have a system which doesn't have a unique inverse. If you have less numbers in z than you do with x, then it's not invertible because you've lost information. So invertibility implies the same number of dimensions. I'm sure there's probably cases where you can impose conditions on the transformation that you're doing, but in general, that's the case. So here's the equation that we have. The density function for z is equal to the magnitude of the Jacobian times the density function, but instead of z1 we put in h1, z2 we put in h2, etc., the inversions. If you look back at the one-dimensional case, it's a generalization of that case. If you looked at this for one dimension, you would find it reverted to the one-dimensional functions of several random variables that we had. Let's take a look at some special cases here. Suppose we had x and y being two IID. Remember what IID means. Independent and identically distributed, zero mean Gaussian random variables. And we're motivated here, for example, by looking at the, say, the velocity in gases, as we talked about. Suppose x and y were the velocities in a gas, and we said that they were Gaussian and independent of each other, and that they were IID. Okay, fine. If we had x and y as being two independent and identically distributed zero mean Gaussian random variables, suppose we didn't want to look at those in Cartesian coordinates. We wanted to look at those in polar coordinates, and rather look at the magnitude of the velocity, or in other words, the speed of the particle, and then also look at the angle associated with the speed. Now, it might be a little bit difficult to envision the density function for v, but what do you think of the density function for w, which is the angle? Well, if it could go to the right or the left with the same probability and up and down with the same probability and they're Gaussian, you might expect w to be a uniform Gaussian random variable from 0 to 2 pi. In other words, it would go one angle just as much as it would another angle. You might believe that. So anyway, this is what we're going to do. We're going to set v is equal to the square root of x squared plus y squared, in other words, the magnitude of this, and w is equal to the arctangent of y over x, which is the corresponding angle. So here are our two functions. We have taken two random variables, x and y, and we have made two additional random variables with them, v and w. And given the joint density function of x and y, we would like to find the joint density function for v and w. Okay? So let's proceed with the formula that we derived. Let's first of all look at the inversions. We know the inversions directly from polar coordinates. X is equal to v cosine, y is equal to v times the sine, right? So these are the inversion formulas. Given v and w, we can get back x and y. So this is my h1, and this is my h2. If we were to look at the Jacobian then, the Jacobian is the partial of x with respect to v, y, v, x, w, and yw. So we need to look at these, and we go back, and let's see, x with respect to v, x with respect to v. Well, if we do the partial of x with respect to v, we just get the cosine, right? The partial of x with respect to w, we get v times the minus sine, etc., right? So we can go back and we can look at the four different partials corresponding to this inverse equation, thereby generating the Jacobian that we have here. And the elements of this Jacobian come by differentiation of these inversion formula. We take the magnitude of the Jacobian, which of course is equal to this times this minus this times this, and we find the magnitude of the Jacobian is just equal to the variable v. We use the trig identity cosine squared plus sine squared is equal to 1. So the magnitude of the Jacobian is equal to 1. So here's our formula. The Jacobian is equal to, the density function for v and u, this again is the polar form, the magnitude and the phase of the polar form, is equal to this expression. Normally I would put a magnitude around v, but v is going to be positive anyway. It's the root of x squared plus y squared, right? So therefore it's going to be positive anyway, so I don't need to put the root around there. So I simply need to look at the equation for f of x and y, and every place I have an x, I substitute the v cosine. Every place I have a y, I substitute the v sine. And I simply have to write down now my expression for a joint Gaussian random variable, which are independent, which means that correlation coefficient is equal to 0. Am I going backwards? Yes, I am. So here is the joint density. This should be a sigma squared here, clearly. It should be a sigma squared instead of just sigma. So now I'm going to substitute v cosine for x and v sine for y, multiply by v, and if I do that, I get this expression. It's not a pretty expression, but it simplifies very nicely. See what I've done? I've taken x, I've substituted this, I've taken y, I've substituted this. Here's my Jacobian in front, and there should be a sigma squared here also. The sigma squared, please follow that down as we go. It was deleted initially, and all of the subsequent steps followed. Well, this is nice because we can take this expression that we have and we can simplify it. We can take the v squared outside. We're left with the cosine squared plus sine squared on the inside, which goes to 1. And we're left with a very nice expression. And the expression is v over 2 pi sigma squared e to the minus v squared over 2 sigma squared. Now, what is interesting about this is looking at the marginals. How do we get the marginals? Here's the joint. This is the joint density function. How do we get the marginals? We integrate out the variable we don't want. So if we want the marginal with respect to w, we integrate out v. Gosh, v isn't even there, is it? Or w isn't even there. So if we integrate out w, this whole thing goes away and we're just left with a constant. Whoa, that's interesting. Well, let's first of all integrate out the w, integrate out the angle. We integrate from 0 to 2 pi, and we obtain this as the corresponding marginal for the speed. This is the magnitude of the polar coordinate. This turns out to be something referred to as a Rayleigh random variable. And indeed, the distribution of the speed in a gas is a Rayleigh random variable. If we generate the other random variable, we find out it's equal to, we integrate the marginal, integrate the joint to get the marginal, and that's just equal to a constant. And that's a uniform random variable, which is what we initially supposed, that the angle is just equally probable to be in any direction that we want. And we've indeed showed that, because it's a uniform random variable from 0 to 2 pi. In addition, if we were to multiply these two marginals together, we would get the joint. If we were to multiply these two marginals together, we would obtain the joint density function, which means that the speed and the angle are independent. Doesn't it make sense that they're independent if x and y is independent? Shouldn't the speed and angle be independent in the sense of having nothing to do with each other? Yeah, it does make sense. So therefore, the magnitude and the phase, the angle, are independent random variables also. Any questions on that? Okay, let's clear our glossy eyes and be back with the big hands on the 6. Okay, we're back. There's one other example about functions of several random variables I would like to tell you about, and that's the idea of using so-called auxiliary functions. Here's the problem. We have already looked at the problem of finding z, well, let's say u is equal to x plus y. We have already looked at a way to do this, correct? And we found out that if they're independent, it becomes a convolution, etc. And we had a specific way of working that problem. I'm going to offer you a second way of doing that problem. A second way is to define v is equal to x minus y. And this is something we don't want to know, but it becomes an auxiliary function and a catalyst for solving the problem. It's a different way of solving the problem than we did before, but it's an alternate way. And now what we can do is we can come down and, using the Jacobian concept, is actually come up with the joint density function of f of u and v given the density function for x and y. But we don't want the density function for u and v. What do we want? We want the density function for u. So we integrate out the v. And we would obtain the same convolution result that we did at our previous derivation. Now, I'm not offering you, as this is a good way to prove that when you add two random variables, you convolve their density functions. However, it should illustrate the use of the so-called auxiliary function to obtain a single combination of number of random variables. And in many cases, this is a very useful way, especially if you're clever in choosing the x minus or the v transformation. So it's almost, in chemistry, they have this the term of a catalyst, that you put the catalyst in to help the reaction, and then when you're done, you kind of take the catalyst out, and overall it has no effect. That's essentially what we're doing. We're putting this v in here kind of as a catalyst to help the math. And in many problems, the best way to do this is using this so-called auxiliary function. We work all the way down, and then we take the catalyst out right here to get our original function. So we can use this broader example to do lower dimensional examples. And even though many times it looks like more work, there's many problems where it's really the only way to do it. So let's go to the overhead. And let me just go through the steps which I have just specified to you. We want to find v is equal to g of x and y. And we define an auxiliary function w. I'm using different variables here, but the concept is the same. So the auxiliary is this catalyst that we put in. And we use the Jacobian transformation to find the joint density function for v and w. And then once we get that out, we integrate out this catalyst, this auxiliary function w, to find the marginals. And there are certain cases where this turns out to be useful. I would invite you to look at the student's t random variable on page 230 of your text in your spare time as an example of doing this. Okay, we are ready for our next AGB. Oh, that is B. Let's run through that. Okay, hold on. Don't panic, that's my job. H. Okay, good. We're going to talk a little bit about some of the preliminary material for courses in statistics, specifically sums of random variables. This is, by the way, starting a new chapter in your book. By the way, homework will be on the web. I'll give it to Hungbo today, and he should have it on the web either later today or tomorrow. It'll be due next Tuesday. Here's the idea of the summation, and this is what we're going to spend this entire chapter on, because believe it or not, it's fascinating. We're going to take a number of different random variables x of k. So this is a vector of random variables that are related in some fashion. We're going to sum them up, and we're going to call that equal to the sum. Now, when we sum up random variables, if this is a random variable, then the sum is also a random variable, correct? The sum is also a random variable. Let's look at the expectation of the sum. Well, the expectation of the sum, expectation is a linear operation. So the expectation of the sum is the sum of the expectations. That sounds like double talk, I know. But if you look at the equation, that's exactly what it says. That the expectation of the sum is equal to the sum of the expectations. So if we're summing up zero mean random variables, say a zero mean Gaussian, all different standard deviations, could be very related to each other in terms of covariances. If each one is zero mean, then the sum also has zero mean. Doesn't matter about those cross terms. This is an equation which is always true. Doesn't matter what the random variables are. What about if we have a Cauchy random variable in here? Well, that means one of these terms is not defined, which means one of the terms in the sum is not defined, which means that this S is not defined, this expectation is not defined. And here's the other interesting point. If the random variables are IID, independent and identically distributed, and each one of these X bars has the same exact mean, then that means that the average of the sum is equal to n, the number of elements that we're summing, is equal to n times the expected value of each component. It's pretty straightforward, right? Okay. Variance. That's a little bit more complicated. Okay, the variance of S is equal to the expected value of S minus S bar. I don't know what the heck that V is. That V should not be there. Let's see if I can rub it off this. No, I don't know. The V should not be there, right? It's equal to that. You go through a bunch of math stuff, okay? And I invite you to go through the math. It's relatively straightforward. And you find out something interesting. It's equal to the summation of the covariances of x, k, and y sub l. You remember the covariance matrix that we talked about when we talked about the Gaussian random variable? That covariance matrix exists no matter what the random variable is. It doesn't have to be Gaussian. That covariance matrix exists. And that is the covariance matrix we called K. If you go to that covariance matrix and you add up all the elements in the covariance matrix, you get the variance of the sum. Because that's what this term is, isn't it? This is the sum of all of those elements in the covariance matrix, that K matrix that we talked about previously. So if you add all of the components of that covariance matrix, you will determine the variance of the sum of the random variables. So that's interesting. The variance and the mean are totally determined by the variance, by the covariance matrix, and the mean of the random variable. You don't need to know the detailed description of the density function of the underlying random variable. All you need to know is the mean and the covariance matrix. If you know that, then you know the mean and the variance of your summation. Let's take a special case of independent random variables. Okay, independent random variables. The covariance matrix is equal to this. Let me elaborate what this means. Have we talked about the Kronecker delta here? You guys, wake up. It's not my fault. I'm exciting to listen to. Okay, Kronecker delta. Kronecker delta, del of k, is the discrete equivalent of the Dirac delta, and it's also an impulse response. It's equal to 1 if k is equal to 0, and is equal to 0 if k is not equal to 0. Okay? Very simple concept. But you'll notice it has a square bracket to notice it's discrete, and also, unlike the Dirac delta, there's nothing infinite about this. This is nice and realizable. It doesn't go to infinity at any place. Now, we want to look at the case now where we have independent random variables. And we want to look at the covariance of x sub l and x sub k. That's equal to the expected value of x sub l minus the mean. Are we assuming IID? Yes, this is just independent. The mean of L times x sub k minus the mean of k. That's equal to the covariance in general. If the random variables are independent, what do we know about these expectations? We can break them up into the product of the expectations. right? And what does this first term equal to? 0. Yeah, somebody said. Exactly. Isn't this equal to 0? Isn't this equal to the expected value of XL minus ML? And aren't they the same thing? Yeah, they're the same thing. So it's equal to 0. The second term 0 also. So if they're independent, this is equal to 0, but there's an assumption that we have made, and that is L is not equal to K. In fact, we have done this here when we have broken this up. We've assumed that L is not equal to K. Clearly, if L is equal to K, the random variables are not independent of each other, are they? They're the same random variable. How can they be independent of each other? So if L is equal to K, we have this is equal to the expected value of X sub L minus ML squared, which is what? The variance of XL. So we have this expression. And you'll notice this expression can be written in terms of this Kronecker delta as the variance of XL times del of K minus L. In other words, it's equal to the variance of XL when K is equal to L. It is equal to 0 otherwise. It's a nice compact notation for writing this. Okay? What does this mean in terms of the matrix? Recall that the K matrix had this as elements. Well, this means that the diagonal of the elements are equal to the variance, and all the off diagonals are equal to 0. So this means that this K, which is the covariance matrix, has the variance of x1, the variance of x2, etc., down the diagonal, and 0 all on the off diagonal. One of the nice things about this, it makes it easily invertible, doesn't it? Right? It's a very easy matrix to invert. So this is true. What's the only assumption that we have made here? The only assumption that we have made is of independence. So when we have independent random variables, the covariance matrix is equal to 0 in the off diagonal terms, and on the diagonal is equal to the variance of the variance of the individual random variable. So that gets back to our overhead, which is the special case where we have independence random variables. We have just shown on the board that the covariance is equal to sigma k squared times this Kronecker delta. Here's the Kronecker delta as we have defined it. Therefore, the variance of S, remember we said the variance of S was given by all of the summation of all of the elements in the covariance matrix? So if we go back here and we look at this as the covariance matrix, and the variance of X is equal to the summation of all of the terms in here, then it's just equal to the summation of the individual variances, because all of the other terms are equal to 0. So this is the reason we can say on the bottom here that the variance of S, of the summation, is equal to the summation of each of the individual variances. The only assumption we have made thus far is independence. We have not assumed identically distributed. If we have IID distributed random variables, and the sum is equal to this, the mean is equal to n times the mean, and in the previous case, what happens if they're identically distributed? It means all of these terms are the same, correct? So that means that the variance of the sum is equal to n times the variance of a component. And so those are the three criteria that we have here. That takes a long time. And the variance is if they're IID, this is always true. If they're IID, we have this relationship. let's look at the characteristic function of the sum of random variables. We've done this a little bit before. Now we're going to do it again a little bit more rigorously. Here's our concept of the sum. We have defined before, we have shown before that the characteristic function of the sum is equal to the characteristic function of the individual components to the nth power if they are IID. Do you recall us deriving this or not? Whoa. Okay. How many recall us deriving this? Okay, see, 5, 6. Okay. If we have the sum equal to the summation of k is equal to 1 to x sub k, I'm sorry, equal to n of x sub k, we have shown that if we have two versions, let's call this S sub n, x1 plus x2, what is the corresponding characteristic, what is the corresponding density of the S? Isn't that equal to the convolution of the two? Right? I'm using shorthand notation here, correct? So if we have S sub 3 is equal to x1 plus x2 at plus x3, and they're independent, what do you think the density function of the sum is? It's a convolution of all of these, right? And if we were to have n sums, if we were to have this, then the characteristic function for n values, I'm sorry, the density function for n values, be equal to f x1 convolved with f of x2 convolved all the way up to f of x sub n. Right? The only assumption here is independence. Now, if we perform a Fourier transform, we know that convolution in the Fourier domain reverts to multiplication. Hence, we have phi of x1 times phi of x2 times all the way up to phi of x sub n. And again, this corresponds to each one of these cases independence. This requires independence. This requires independence. This requires that the random variables be independent, and this requires the random variables be independent. So for that case, the characteristic function is equal to the product of each one. Now, if each one of those is an independent random variable, then each one of these is exactly the same. In other words, if they are not only independent, but if they're identically distributed, then phi of x1 is, say, phi of x. Phi of x2 is also phi of x. Why? Because they're identically distributed. So they all have the same characteristic functions. They all have the same density functions. They all have the same characteristic functions. And so clearly this is nothing more than taking the characteristic function for x, and since we have n terms here, we're raising it to the nth power. Hence the equation that I have on the PowerPoint slide. Say, are you comfortable with this then? Okay. So the characteristic function is equal to the characteristic function of an individual component raised to the nth power. The other interesting thing, of course, is the second characteristic function is equal to n times the second characteristic function. Does this look familiar to you? Yeah? Okay. Here is the interesting result. If S is Gaussian, we've stated this before, we're going to show it now. If x is Gaussian, the x sub k's are Gaussian. If s is Poisson, the sum is Poisson if the x sub k's are Poisson. So as we have stated before, these random variables have a property, many of them, to actually generate themselves. If you add up a bunch of binomial random variables, you get a binomial random variables. The coefficients are different, but nevertheless it is a Gaussian, I'm sorry, a binomial random variable. And we did some of these in a previous lecture, is that correct? Okay. Which one do you want to do? I think we did Gaussian, we did Poisson, and we did binomial. I remember doing binomial. We did Cauchy. I remember this stuff. How come you don't? Okay. So we've done that. Okay, let's look at the average sample mean. Many times you have a number of random variables and you attempt to characterize a vector of random variables by a single number corresponding to their average. The average is obtained by taking the summation of the random variables and dividing by n. That's the average. You'll notice that the average is nothing more than the sum divided by n, correct? The average is equal to the sum divided by n. Now, the average, hopefully, is an estimate of the underlying mean of the random variable. In other words, you would hope that the average would be a good estimate of the actual mean of the underlying random variable. Let's look at this. Let's look at the characteristic function of the average. The characteristic function of the average is equal to the expected value of e to the j omega a, right? That's the definition of the expected value. However, this is equal to the expected value of e to the j omega s over n. How did I get that? Because the average is nothing more than s over n, right? Let me go to the board here for the next one. The expected value of, the characteristic function of the average is equal to the expected value of e to the j omega s over n, correct? Which is the same thing as the expected value of e to the j omega over n times s. Well, we know what this is. We know that this is phi sub x raised to the nth power. It's exactly the same as a characteristic function for the sum, except that instead of omega, we put an omega over n. This, then, is the characteristic function for the average. Characteristic function for the average of IID random variables. And again, it's important to put that restraint or constraint upon the problem. That the characteristic function of the average of the random variables in relationship to the characteristic function of an individual component of the IID sum. And the reason that I hesitated here is because, so I shouldn't have hesitated. The phi sub a is equal to phi sub s of omega over n. And we've actually gone to the next step. This is a characteristic function of the sum. Therefore, the characteristic function of the average is the equation which I have here, which I have just derived right here. Okay? What are the assumptions? The assumptions are IID random variables. And this is always true. So let's take a look at the average. If the samples are IID, we have just shown this relationship for the characteristic function of the average. We can also look at the second characteristic function. Remember we said that that had some very nice computational quantities, right? Everybody wake up. Should I start throwing stuff? Aren't there profs that throw stuff when you doze off? Just the fear should wake you up. Okay. So we have the characteristic function. The second characteristic function is given by the logarithm of this, which is given by this equation. We therefore get to some very interesting results. What we want to do, by the way, let me tell you what we'd like to do. What are some of the characteristics you would like of the average? You're summing up a bunch of random variables. Each of these random variables has a mean of x bar, right? They're IID. Wouldn't you like the expected value of the average to be the expected value of x, one of those components? Isn't that, in fact, what you're trying to do when you compute the average, is figure out what x bar is? Indeed, that's the case. You're using the average to estimate the mean. You don't know what the mean is. You know it's there in the distribution somewhere, but you don't know what it is. You'd like to estimate it. How do you estimate the mean? You do it by the average. In fact, it's such a common thing that many people call the average the mean. We're distinguishing in here as the average being a random variable and the mean being a fixed underlying parameter. Here the mean is unknown and we're using the average to compute the mean. So with this, what would you like the average, the expected value of the average to be equal to? You would like it to be equal to the mean of x. And then what would you hope to as n increases? Why in an average don't you trust an average if there's two numbers you average together? Why do you trust that less than if you average 1,000 numbers together? Wouldn't you assume the average of 1,000 numbers together that were IID would be more accurate than if you just averaged two of them together? It would be a better estimate of the mean. How do we capture that? Well, A is a random variable. It has a variance. It has a mean and a standard deviation. What we would hope is that n went up, that the standard deviation of this average would go down, smaller and smaller and smaller and smaller. And indeed, asymptotically, as the number of observations become infinite, that variance should go to 0, and we should know the mean exactly. If we took a Google values in our summation, right? That variance would be very, very small if they were IID random variables. So this is what we're going to look at. We're going to use this characteristic function to first of all compute the mean of the average. Now that sounds strange, but it makes sense, at least in this course. The mean of the average, the expected value of the average, and we're hoping that the expected value of the average will be the expected value of x, because that's what we're trying to figure out anyway. Then we will look at the variance of the average, and we will hope to find out that the variance of the average in some way decreases as n increases so that we can be more and more certain that that average is an estimate of the mean. You follow? Okay, so that's the reason that we have computed for IID, random variables, the characteristic function of the average, and the second characteristic function of the average, because it is from these that we will compute the mean and the variance of the average. So let's compute first of all the mean of the average, and we do that by taking the first derivative of the second characteristic function, and we find out by evaluating the first derivative at the origin, if you remember that, and we find out that indeed, by computing the first derivative of the origin, that the expected value of the average is equal to the expected value of x. Exactly what we wanted, because that's what we're trying to do anyway. If your average didn't give you the expected value of the mean, you would never be using averages. You would be using something else. So that's true for IID random variables. So at the bottom you could just see, as it should be. Now we would like to look at this variance of A by taking the second derivative here. So let's take the second derivative and evaluate it at 0. And if you remember, we take the second characteristic function, we take the second derivative evaluated at 0, we get minus the variance. So that's what we're going to do. We're going to take the second derivative at 0, we get minus the variance, and we find out something very interesting, that the variance of the average is equal to 1 over n times the variance of x. Remember what we wanted to do to make sure that the average became more and more accurate? We wanted to make sure that that variance of the average became smaller and smaller and smaller as n increases. It does. The average becomes smaller as 1 over n times the number of samples we take. So if we take 1 billion samples, 10 to the 6th, then the variance of A is going to be 1,000th well, I'm sorry, the variance, the standard deviation, which is actually what we like to measure. The standard deviation will be, what did I say, the square root of that, okay? So this is very nice and makes intuitive sense. So we do and see that the average behaves the way that we would like to, but now we have a quantitative measure of how much it behaves. If we go from 10 to 100 samples, we now have an equation which can tell us how much more accurate our average is going to be. So here's an illustration of what we have just derived. Here's the underlying value of x. Now, we have a variance of x, which is a measure of how much it's spread out. Actually, the standard deviation has the same units of x, so we use the standard deviation for how much it is spread out. And what we have shown is that this density function is centered at x bar. And we have shown that the average, as we take more and more samples, is going to get a smaller and smaller standard deviation, and it is going to bunch up around the mean because the standard deviation becomes smaller, but the mean is always the same. Remember, the mean wasn't a function of x. It was always equal to x bar. So it becomes smaller and smaller and smaller. So we have this situation. What does it kind of become in the limit? What if you take a density function, you squeeze it together and puff it up? It becomes what? A Dirac delta function, always. Any function which has a unit area, if you push it together and you puff it up in such a manner as to maintain that area, you will, in the limit, go to a delta function. Now, we can actually apply the Chebyshev inequality. Remember the Chebyshev of inequality? To the average of IID random variables. This was the Chebyshev inequality. Except now we're going to apply the Chebyshev inequality to the random variable A. The Chebyshev inequality, which we derived way a long time ago, was applicable to any random variable. The Chebyshev inequality says the probability that A minus A is less than epsilon is given by this bound. Again, it's something that we derived previously. But here's something interesting. We have now an expression in the Chebyshev inequality for this variance of A. We've just derived it. It's equal to the variance of x over n, right? So A bar is equal to x bar. The expected value of the average is equal to the mean. And the variance of the average is equal to 1 over n times the variance. So here is the Chebyshev inequality. The probability that the average minus the mean, and don't forget what we're trying to do. We're trying to use the average to estimate this mean. So what would we like this probability to become? 0, right? We'd like that probability to be 0 if A is equal to x bar in some stochastic sense. So the probability that your estimate of the mean, your average, minus the true actual mean is less than epsilon is given by this bound. And you'll notice what happens in this bound as n goes to infinity. As n goes to infinity, this becomes 0. So the probability that your average goes to your mean in any interval is greater than or equal to 1. That's pretty good if you have a probability greater than or equal to 1, right? Clearly that means it's equal to 1. This means you converge in a way called improbability to the average being equal to the mean. It's not that the average is equal to the mean. It's equal to the mean in this sense, in this piece of math. This is something which we will call the weak law of large numbers. And we actually used it before. Remember when we were throwing darts at the dartboard with all the circles? And we said if we threw enough darts, that if we counted the number of darts that we got in the middle of a circle, divided by the number of darts that we threw, we would come up with pi, what was it, pi over 2? Pi over, do you remember that? It was pi over 2. You remember that. We started it way at the beginning of the course. We had all these circles. We had all of these circles, and we said that if we took a random point within a circle as opposed to the circumscribed box, gotta be careful, that this is equal to 2a squared over, let's see, pi r squared, so, or pi a squared, so it's pi over 4, right? So that was the probability. Then we said in an illustration of Monte Carlo simulation that if we took darts and we threw it at a dartboard which looked like this, and we did it 1,000 times, that we could take the number of times it was in the circle divided by the total number of times thrown. That would be approximately equal to pi over 4. Way at the beginning of the course we did this. We were assuming here the law of large numbers. We were assuming that the average that we would obtain by repeated Bernoulli trials in this experiment, that this average would approach the true mean, which we could calculate offline. So actually we have been assuming, way back in the relative frequency definition of probability, we assumed a law of large numbers. We assumed that the average would approach the mean. Now we have proven it. So it's the weak law of large numbers, and here is the weak law of large numbers. That for any epsilon greater than 0, sounds like a math class, I know, but the probability that A is the average minus the actual mean is less than any positive number you give me. I can find you a value of n, and this will approach 1. So no matter how much I squeeze together this interval, I can make epsilon 10 to the minus thousandth. I can always find an n big enough so that I can approach a probability that the average is equal to the mean. And when we say this, we mean it in this sense, and in this sense is referred to as the weak law of large numbers. So the average, in this sense, approaches the mean. And we've proven it. Even though we kind of knew it intuitively, we've now proven it. There's a stronger statement, which is referred to as the strong law of large numbers, which says the probability that the probability of the limit being equal to the mean is equal to 1. We won't go into the derivation of this. It's a little bit more complicated, but is actually a stronger statement of the law of large numbers. But we all know as engineers what this is trying to say, that the average approaches the mean. That's what the law of large numbers is saying. Let's look at an example, and maybe we should start with this example next time. I'm going to call it sloppy confidence interval on Bernoulli trials. And I'm going to, hold on. I wanted to find out how many movies I've watched in my life. So I got Leonard Maltin's book on movies, you know, where he reviews all the movies. And there were like 40,000 movies in there. And I randomly chose maybe 1,000 of them, right? And then I said, I saw them or I didn't. Now, that's a Bernoulli trial, right? Now, there's an underlying mean in that book of how many movies that I've seen. But I'm not going to go through the whole book. But I can look at 1,000 of those movies. Each one's a Bernoulli trial. Yes, I've seen it. No, I didn't see it. And I can estimate to within a certain degree of accuracy using the Chebyshev inequality the number of trials, the number of movies I have to look at to say something like, well, the probability that I've seen that I've seen 50, say a third of the movies in the book, the probability that that's true is greater than a certain percentage. So I can say with a certain confidence the number of movies that I've seen. So I did that, and you'll find out how many movies I've seen next time we meet. Any questions at all? Okay, thank you. We'll see you then on Thursday.